How many stirrers do you see? The beaker and water act like mirrors and lenses to confuse us. The experiments with water and colored oil are a simple way to show some aspects of a method to collect 1 million gallons of petroleum spilled anywhere in the oceans. One pulls water out from under the oil pool to make a surface current that pushes the oil together. Last time the message was in the words with video as background. This time we will try to explain the videos and their meanings. We see a stir and a depression, a dimple in the surface. If we replace air with colored oil, the dimple should deepen into a cusp. Because the oil is heavier than air, we might do experiments in Lake Ontario without oil present. If we could find a relationship between the depression of water by air alone and the oil depth for the same conditions using oil and water. Oil is poured into the cusp and broken into droplets. The motion of the droplets gives us, more or less, the motion of the water. The needed surface current is formed to push the oil together. Spiral motion of water down the impeller is implied by the oil droplets near the cusp. The other flows out of the bottom and up the walls is not shown. Okay, but a cusp is of the wrong shape to hold 1 million gallons of oil. It is of small radius. Its surface area and its volume is tiny. We want depth near the edge of the pool or over the entire pool. What would happen if we reverse the flow using, for example, a propeller or air bubbles instead of the magnet to move the water up in the center and flow down the walls? Where would the oil go? Centrifugal force separates cream from dairy milk and extracts water from swimsuits. A huge ship went to the Gulf of Mexico to use centrifugal force to collect oil. Do we need centrifugal force? Do we have very much centrifugal force in our experiment? To see centrifugal force, place a beaker with water and oil on a turntable, or model it. This is a crude approximation. I took the beaker in my hands, swirled it around, put it down, and started the cameras. Does it look at all similar to our beaker tests? We start again with fresh water and the stirrer going. Where's the dimple? We pour water in, but there's a delay in forming the cusp. The cusp is not even over the stirrer. So I was wrong in expecting a simple relationship between air and oil. But hey, this is better. A relationship works for higher power and mixing, but less power is cheaper and we don't want mixing. It raises a question as to what is happening between the oil and water. The delay gives it time to happen. Maybe I can explain it in the next episode on technical matters. Let us try to visualize something more complicated to get a better picture of our intention. Consider 2 beakers with the small one is suspended inside the large one under water and oil. A magnetic stirrer on the bottom of the big one throws water out along the bottom. The water still goes up the wall of the big one, but where will the water come back down, and where will the oil collect? Think about it when we do the hand waving. The hand waving will explain how to change the oil pool shape, and our next episode will go into the technical details. The beaker experiments show the advantage of beaker walls and bottom and the accumulation of momentum. The accumulation is shown when we start with the oil still on the surface or stop the stirrer by unplugging the motor. Let's look at the delays when we stop or start with the oil present. Watch the drops under the oil pool. When we stop the oil, they continue to rotate while the cusp disappears quickly. The surface is still rotating. Skip to a stationary surface with 1 drop to watch. The stirrer has been running faster than before, and the drop begins to circulate. Soon a tiny cusp begins to form and form quickly. The drop moves down the cusp to the tip and beyond. The flow speeds up, and even the stirrer turns faster. The 1960s idea of sweeping oil together was to use energy to pull water out from under the oil. The energy is used up. The beaker accumulates energy as motion develops. Ocean waves slowly accumulate or lose energy while the wind blows or ceases to blow, both over long times and distance. Google wave and BEAUFORT or LUD. Beaufort's observations were for the war with Napoleon. Ledge tables help surfers today search for big waves using weather. If any of you are surfers and have a short video of a big wave breaking or being ridden, I would like to use it in my next Black Gold or Black Death number 3. Let's watch one of 6 editions of oil. As we add more water, the depth changes. But as we add more oil, the size of the cusp doesn't seem to change. Did the cusp get longer? Look more closely. There are 2 big bubbles held by the water flow down. Maybe water flowing down, pulling the drops, interferes with coalescence. Friction and turbulence consume energy. There is friction between a stirrer and the beaker. Friction for flow along the beaker surface, less friction between the oil and water, and very little friction at the air surface. Turbulence is a confusion of velocity and direction which depletes the energy. Consider energy loss for flow in a tube, a hurricane, or in our beaker. A Newtonian fluid like water and air flows at a minimum pressure drop in a straight tube if the flow moves parallel to the wall. The fluid moves fastest in the center, and at every radius the friction with a larger radius is the same. That is, the flow is slower. The wall doesn't move, nor does the fluid in contact, but the increase in velocity as the radius decreases, velocity gradient, is maximum to provide the same frictional force against the flow. Osborne Reynolds, in the 1800s, injected ink at a point in the net tube and saw a straight line when the flow was laminar. When he increased the velocity, the line broke up downstream and spread throughout the tube. This caused the pressure drop, that is the energy loss, to increase by an order of magnitude. He found that whether laminar flows or turbulent flow was stable depended on a ratio of viscous forces to momentum forces. His ratio, the Reynolds number, is 2100. Turbulence varies greatly. A theory to explain friction and heat transfer for turbulent flow used a thin viscous sublayer on the wall which was laminar and had a velocity gradient steep enough to give the frictional force. In the core, the gradient changes with time and location and is small. We can get a better idea of the water flow if we add oil with a green dye that dissolves in water to the oil cusp. I am adding the green oil. Look for a sort of dark green cloud. It will take a while for the green to go through the oil to the interface. The green is coming out of the tip now and flowing down from the cusp. It seems first to hold on to the cusp tip and then to form a stream of threads. Where it goes next is not so clear, but we can watch the rest of the water turn green slowly. See the wave of green spread over the bottom? Alternatively, we can add droplets of green oil directly to the beaker. We can watch the droplets move and we can watch the green color spread, which was laminar and had a velocity gradient giving the frictional force. For 70 years, scientists tried to measure this layer. I heard a lecture about photographing particles in the flow. Someone said the particle is moving 50 times too fast, but a particle is not fluid. One of my proposals from Michigan in 1960 to NSF was a method of using light to draw lines across a moving fluid to observe real fluid flow. The proposals were rejected. My student Aristotle T. Popovich and I obtained the first real statistics of the thickness of the viscous sublayer published in 1967. Look it up under Popovich in Citation Index and see if it is still being cited. A perfect hurricane takes air and humidity from sea level, temperature approximately 300 degrees Kelvin, up to 17 kilometers. temperature approximately 200 degrees Kelvin, adding heat of water condensation on the way up. Its Carnot efficiency approaches 30%. From space, the Hurricane has a small circular eye expected for perfection. If the rotating winds tangle, the eye's shape changes or breaks up, and the Hurricane's power drops greatly to a lower category. In our stirred beaker there wasn't a dimple, but there was a shimmer of instability. Possibly a blob of water from the left was moving fastest and pushed past the center line at some time. The flow was not well coordinated. I would like to try to relate what we've seen in the beaker to what we would be doing with 1,000,000 gallons of oil. Obviously the cusp is tiny and we need a big, large pool. It is of interest to us is the impeller throwing the water out the bottom, up the walls, and then converging to the center and the surface. The reason the converging is important is because that increases the velocity of the water. If the water's velocity is high enough, it will push the oil ahead of it. What happens is that you'll form a cusp of a certain diameter, depending on the flow rate, and the cusp will help the flow down, so the flow is much more efficient. Now what I want to do is to expand this from the beaker to the real world. I want to take my arms out, maybe 30 meters, maybe 100 meters, and have a small circulation, well, not that small, we're talking meters now, that's going exactly like we had before. In at the surface, out at the bottom. So that what we're doing is we're compressing a pool of oil together. This experiment was photographed both from above and the side. The stir is still and the surface is almost still. The stir starts up after a delay of 10 seconds and the surface responds 10 seconds later. You saw the stir start. 10 seconds later, a gathering in the center shows the cusp beginning to form. You'll also see, along with the circular area, the oil moving in toward it, and it's a little bit turbulent toward the center as well. After a minute from the start, oil-colored green is added, and we switch to a side view beginning again. The side view goes on in total for 14 minutes to show the green dye dissolving in the water, but we will switch back first. Right now the oil is being injected, the green dye is being injected. You can see the dark cusp, which makes it easier to see the cusp. You can occasionally see the tip of it sticking out, and we're about to shift to the side view. There's the side view. Again, the stir is still, the surface is almost still, and then we will go to a magnified version of this. You notice not much is happening. That was a continuation in time. There's still not much. There it goes. You can see the cusp beginning to appear. In fact, actually it's growing and growing as it pulls oil in from outside, and you can see little blobs on the surface slightly. Not nearly as well as we can see from above. This will run until we inject the blue-colored or the green-colored oil. The cusp, of course, is not quite steady. There is the oil coming in. We'll see it go down in and make a dark cloud inside the cusp. And there we're back to the top view again for the second injection, I think. Note that the oil is circulating freely outside the center, bouncing off one another, but that the oil does not seem to touch the side completely, certainly doesn't leave a stain, and the oil seems to be going faster toward the center than it is to the outside. The outside is falling behind.